Let's look at an example. So often people have sucrose in their diet, and the hydrolysis of sucrose will form glucose and fructose as part of this digestive process. And we can think about the rates at which that would happen in the body. So normally, we're at 37 degrees. That's normal body temperature. And we have the observed rate constant for that is 1.0 times 10 to the minus 3 per molar per second. But what happens if your body temperature is lowered? What happens if it was at 35 degrees? And to be able to answer that question, you need to know what the activation energy is for this process. And here it's 108 kilojoules per mole. So we want to ask the question, what is the new rate constant at 35 degrees? So we can take our Arrhenius equations, and we can put a 1 by the rate constant for temperature 1 and a 2 for the rate constant at temperature 2. Now we can combine these equations. Natural log of A cancels out. It's not temperature dependent, so it doesn't stay in here. And so we can solve. We can subtract these two, or that's equivalent to dividing them. And so natural log of rate constant 2 over rate constant 1 equals minus the activation energy over the gas constant times this temperature term. Does this look at all familiar? Does this look like some other equation you saw once upon a time? Do you remember what that equation was called? Van Hoft equation, right. And there we were comparing what instead of rate constants? Equilibrium constants, and instead of EA, what term did we have here? Delta H, right. And it's good you remember that because we're going to come back to that at the end of today's class. So we can use this equation and plug in the values. We put it in our activation energy, and remember to pay attention to units, because if you're going to cancel your joules with the gas constant, you want to make sure you've converted your kilojoules to joules, and then we can plug everything in and solve for K2. So here K2 is 7.6 times 10 to the minus 4 per molar per second, so it's